As Dallas prepares to serve as a high-tech host city for the 2026 World Cup, the region faces a severe engineering test. The area is slated to host 9 matches over the course of the tournament, culminating in a highly coveted semifinal. The venue selected to handle this volume is AT&T Stadium, temporarily rebranded as Dallas Stadium to comply with international sponsorship rules. But the selection presents an immediate physical problem. This enclosed, climate-controlled facility was engineered specifically to house synthetic NFL turf. This 3D wireframe model shows the baseline layout of AT&T Stadium. The narrow gridiron footprint directly conflicts with FIFA's strict physical mandate, a sprawling 105 by 68-meter natural grass pitch. When we overlay those exact international pitch dimensions onto the existing field layout, the spatial mismatch is obvious. The wider soccer surface collides directly with the lower seating bowl structure, specifically at the corners and along the sidelines. Resolving these structural conflicts and installing the necessary support systems requires a total capital expenditure of $295 million. Crews must literally engineer a complete biological ecosystem from the concrete up. Achieving a FIFA-compliant venue requires re-engineering existing civic infrastructure to support a high-performance environment for living grass. The first phase of this process requires permanently expanding the stadium's internal geometric envelope. Looking specifically at the field-level suites on the north and south ends of this 3D stadium model, we find the primary structural obstacles. To create the necessary horizontal width, construction crews are systematically demolishing and retracting these entire suite blocks. Once the ends are clear, the focus shifts to the 4 corners of the stadium bowl, which present a secondary collision risk for corner kicks. Engineers are carving out 3 feet of concrete from each lower section to ensure proper clearance. Expanding the horizontal footprint creates an entirely new physical problem. The playing surface must now be elevated to seamlessly align with this wider boundary. A higher field plane is necessary to clear the remaining retaining walls and ensure proper sight lines for fans sitting in the lower rows. To achieve this physical alignment, the entire pitch surface is elevated exactly 24 inches above the concrete floor. This vertical shift entirely eliminates the original operational level used by the Dallas Cowboys. Forcing a standardized international pitch into a bespoke regional stadium mandates permanent physical alterations to the venue's massive core architecture. With the concrete shell expanded, the next phase relies entirely on subsurface agronomy. Natural grass placed directly over an impermeable concrete floor dies rapidly. The roots suffocate from a lack of oxygen, and trapped water rots the system. This microscopic cross-section details the foundational solution. Crews install a rigid honeycomb layer called permavoid horizontally across the concrete base. This layer operates as an active vacuum ventilation system, pulling oxygen directly through the root zone. At the exact same time, it actively regulates moisture, wicking away excess water to prevent pooling on the rigid floor. Once the ventilation base is set, crews deposit specialized soil. 10 solid inches of sand are poured over the honeycomb structure as a primary rooting medium. As it settles, irrigation piping is embedded directly into the layer to maintain precise hydration. The system is capped with a highly specific blend of Kentucky bluegrass and ryegrass sod, harvested in Colorado and transported directly to the state of Texas. By stacking active ventilation, sand, and irrigation, engineers effectively fabricate the Earth's natural geological soil mechanics inside a closed loop. Even with healthy soil, temporary indoor pitches have a history of failure, often suffering from loose sod seams that cause players to slip and create massive divots. To combat this, specialized machines plunge thousands of metallic needles directly into the sand base, injecting over 18 million synthetic green fibers. This mechanically stitches the grass seams together, effectively anchoring the entire root structure. The final obstacle is entirely atmospheric. The stadium's enclosed roof completely blocks the natural sunlight necessary to keep the grass alive. The solution is a massive array of LED grow lights deployed to mimic solar radiation. This architectural diagram illustrates a unique engineering choice, suspending the lighting rig directly from ceiling trusses, high above the video board. To maintain photosynthesis, it casts bright pink light onto the field 12 hours a day, acting as the ecosystem's biological heartbeat. When match day arrives, the entire lighting rig is winched up and cleanly out of sight to strictly preserve spectator sightlines. Achieving a world-class natural pitch indoors ultimately requires replicating both the physical stability of the Earth's crust and the exact wavelength of the sun. The effort inside the stadium is intricate, but the $295 million capital expenditure serves as an anchor for a much wider regional mobilization. Over the course of the tournament, between 300,000 and 400,000 unique visitors will enter the Dallas urban grid. This topographical map highlights the specific mobility vectors required to absorb that volume across the Dallas-Fort Worth region. The $150 million Cotton Belt multi-use trail provides a critical new transit artery to handle the surge. Regional authorities are also deploying major expansions to the DART transit systems, built specifically to shuttle fans from training base camps to the stadium. The return on these investments becomes clear when analyzing the tournament's direct economic output. This bar chart compares the initial two. As Dallas